Welcome back to the deep dive. Today we are looking at a problem that has stubbornly persisted even as we sit here in 2026 with tools like, GPT-5 Codex and Claude Sonnet 4.5.
Right.
We have these incredibly powerful models that can write complex boilerplate in seconds, pass the bar exam, and simulate empathy. But there is still this one specific wall they just keep hitting.
The agentic gap.
Right. The difference between just writing a snippet of code and actually acting like a programmer, I mean, you know the scenario.
Right.
You ask the model to build a feature, it writes the code, you run it, it errors out, you paste the error back in, the model says, apologies, here's the fix, and then it gives you the exact same broken code, maybe with a different variable name.
The confident loop of doom. And it happens because despite all the advancements in, parameter count and training data, the fundamental architecture of these models hasn't really changed how it handles its own uncertainty.
Yeah.
It doesn't know how to stop, look at what it just wrote and think, wait, that doesn't actually make sense.
It lacks metacognition.
Exactly. Thinking about thinking. And that is the focus of the research we are unpacking today. It's a paper from a team at the University of Luxembourg titled A Pipeline for Assessing Metacognitive Reasoning in Energy-Based Transformers While Generating Code.
Okay, energy-based transformers. That sounds like we're talking about power grids or something, but we're not.
No, not at all, though the metaphor of energy is actually central to the math. The researchers, Taylor Malloy and her colleagues, are basically proposing that if we want AI to move from guessing the next word to reasoning through a problem, we need to shift from standard probability models to these energy-based transformers, or EBTs.
Okay, so before we get into the whole energy part, let's establish why the current way, the way GPT-5 and all the others work, is failing at the specific task. We usually assume these models are just probability engines, right?
Right. Standard large language models are built on what's called a softmax function.
Softmax. Okay, let's break that down for a second, because not everyone listening is a machine learning engineer.
Sure, of course. So imagine you have a pie. That pie represents 100% probability. The model has to slice that pie up among all the possible next words in its vocabulary.
Okay.
And the rules of softmax say those slices must add up to exactly 100%.
So it has to pick something. It can't just pass.
It has to. And this is the trap. Let's say the model is trying to solve a really, really hard coding problem, and every single option it considers is actually wrong. In a softmax world, the model still has to assign the biggest slice of the pie to the least wrong option.
Ah.
It might be 99% confident in a terrible answer simply because all the other options were just slightly worse.
So it's grading on a curve. It can't just say, hey, this whole pie is made of mud, I'm not eating it.
Exactly. It creates this artificial confidence. The model essentially says, I am statistically certain this is the answer, when in reality it's just the best of a really bad bunch. This is why they hallucinate so confidently.
They're mathematically forced to.
They are. And this is where the energy-based transformer is different.
Fundamentally different, yes. EBTs don't deal in normalized probabilities that have to sum to 100%. They assign a scalar value, just a raw number called energy, to the input-output pair.
And what does energy measure in this context?
It measures compatibility or conflict. And the rule is simple. Lower energy is better. You want to minimize the energy.
Okay, so think of it like tension.
Yeah, that's a good way to put it. If the code fits the problem perfectly, the energy is 0. If the code is total garbage, the energy is really high.
But because it's not a pie chart, the model can look at 10 different options and assign high energy to all of them?
Yeah.
It can say, these all stink.
Precisely. It can effectively say, I hate all of these. It isn't constrained by that normalization. And this allows the model to model uncertainty in a way standard LLMs just can't. It can distinguish between, I know this is right, which is low energy, and I'm just guessing because I have to, which is high energy.
Okay, that makes sense conceptually.
Yeah.
But the paper focuses on metacognitive reasoning. So how does having an energy score turn into thinking about thinking?
It comes down to how the model navigates what the authors call the energy landscape.
Right. This was the visual in the paper that really clicked for me. It's such a great way to think about it.
It is. So imagine a 3D terrain. You've got hills, valleys, peaks. The model is like a ball rolling across this terrain. Its goal is to find the lowest point, the global minimum.
And that's the correct code.
Exactly. The ball rolls downhill. Gravity is the optimization process.
Right. So in a simple problem, it's just a smooth bowl. The ball rolls straight to the bottom. Easy.
Okay.
That's your system one thinking. Fast, intuitive.
But coding problems aren't smooth bowls. They are rugged landscapes. They have these deep valleys, but they also have these little shallow dips, these local minima.
The traps.
The traps. A local minimum is an answer that looks right, sounds right, maybe it even compiles, but it isn't correct.
The paper gives a really specific example of this that I think we should walk through because I feel like every Python developer has made this mistake. The one with the pandas data frames.
Oh yeah, the classic iteration trap. So the context is you have a data frame called data, and you want to loop through it. The model starts generating for row in data, and now it needs to predict the method.
And the correct method, the global minimum, is .iros.
Correct. But there is a very, very seductive local minimum nearby, .rows.
Rose.rows, it sounds so plausible.
It does. Linguistically, it's perfect. For row and rows, it matches the variable name, it follows standard English grammar constraints. If you look at it through the lens of a text predictor, it has very low linguistic energy.
So the model sees that shallow dip and just rolls right into it.
It rolls in, settles down, and says, low energy, I'm done. It stops searching. Even though functionally that method doesn't exist, the code will crash.
But the model is stuck in that shallow valley of just sounding correct.
This is that grammatical hallucination we talk about. It prioritizes sounding like a human over thinking like a compiler. So the core problem here is that once the ball settles in that shallow dip, a standard model has no mechanism to climb back out. It's happy there.
Right. It's good enough for a probability engine. To get it out, you need to jolt it. You need to inject energy into the system to push the ball out of that dip so it can keep exploring the landscape and find the actual deep valley of .arrows.
And that jolt is what this paper is proposing as the mechanism for reasoning.
Exactly. And this brings us to the parallel with Daniel Kahneman's work System 1 versus System 2 thinking.
We hear this comparison a lot in AI, usually just as a metaphor. System 1 is fast, System 2 is slow. But the authors here aren't just using it as a metaphor, are they? They're trying to actually operationalize it.
Yes, they are turning it into a compute strategy. Standard generation is System 1. It's that initial roll down the hill. System 2 is the deliberate effort to verify and correct. And in their architecture, this is achieved through inference time compute.
Inference time compute. This is a buzzword we've been hearing a lot more of lately.
It is, but it's crucial. For years, the dogma was, if you want a smarter model, you train it longer. You spend billions on GPUs during the training phase. Once the model is trained, that's it. It is what it is.
The brain is frozen.
Right. But inference time compute says, no, let the model think longer while it is answering the question. Don't just spit out the first token. Spend computational cycles verifying and refining before you commit.
But wait, hold on. Spending more resources? That just sounds like a polite way of saying slower and more expensive. If I'm running a massive code base or a customer service bot, do I really want my AI stopping to ponder the philosophical implications of every single function?
That's the critical trade-off. And the answer is no. Of course you don't. You don't want an engaging System 2 for hello world. You want an engaging System 2 for complex logic.
Okay.
And that's why EBTs feature what the paper calls dynamic compute allocation.
It chooses when to think hard.
Exactly. Because the EBT generates an energy score. It has a built-in confidence meter. If the energy is super low immediately, it says, I know this. System 1 is fine. Output the text.
Easy peasy.
But if the energy is hovering in a weird middle ground, or if a feedback loop is triggered, it says, wait, this is high energy. I need to spend more compute steps to minimize this.
So it's like a chess player. They play the opening moves instantly, bam, 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 but then they hit a complex mid-game position and they sit on their hands for 10 minutes calculating all the variations.
That's a perfect analogy. The EBT mimics that clock management. It allocates the GPU cycles where the difficulty actually is.
Okay, so let's look at the pipeline they actually built to test this. They have these two algorithms, Algorithm 3 and Algorithm 4, which sound very dry, but they describe a really interesting interaction.
Algorithm 3 is the human-in-the-loop scenario. This is the direct intervention.
This is me yelling at my screen.
Effectively, yes. So the model generates that plausible mistake.
Revs.
You, the human, act as the verifier function, which they denote as y-tellers. You flag it as wrong.
Right. Now, in a standard model, if I say wrong, it usually just panics and guesses randomly. Sorry, how about .getTrows?
Right, it just hallucinates a synonym. But in the EBT pipeline, your feedback, your wrong, does something mathematical. It updates a hyperparameter called $.
And dollars is the number of steps.
Yes, the optimization steps, the thinking time. When you reject the answer, the system basically says, okay, the current energy minimum you found is invalid. Increase in $. Run the optimization loop for, say, 50 more times.
So it's literally forcing the ball to roll for longer.
It's adding momentum. With those extra steps, the model can climb out of that dot rows, dip, explore further across the landscape, and theoretically settle in to the true global minimum of dot arrows.
That distinction is huge. I'm not saying use iteros. I'm saying think harder.
Precisely. And then algorithm 4 takes us a step further and removes the human. It introduces an LLM-assisted assessment.
So we have a second AI grading the homework of the first AI.
Yes, a checker model. But here's the nuance. The checker has confidence thresholds, $2 and $2. It looks at the code generated by the main EBT. If the checker is totally confident the code is right, it does nothing.
System 1 prevails.
But if the checker's confidence falls below a certain threshold, say it's only 60% sure this code works, it triggers that same increase in null dollars. It forces the main model to take more steps.
So if the checker's a little skeptical, the main model has to think a little harder. If the checker's totally lost, the main model has to think a lot harder.
It creates a dynamic feedback loop. The depth of thought is directly correlated to the perceived difficulty of the problem.
This really feels like it solves that runaway train problem. The model isn't just barreling forward generating tokens, it has a conductor checking the brakes.
And importantly, this happens before the code is even shown to you. The idea is that the code engineering team, which is how the authors describe this multi-agent system, hashes out the uncertainty internally.
The code engineering team. I like that phrasing. It implies collaboration, not just a tool.
It does. And it changes the role of the human developer. The authors talk about a future where we aren't just prompt engineers, but process engineers.
What does that shift actually look like?
Well, right now, if a model fails, you just tweak the prompt, right? You say, you are an expert Python coder, please don't mess up this time.
Which feels like superstition half the time, yeah.
It is. Process engineering means we would be designing these energy landscapes. We would be setting the thresholds. You might say, for this critical security module, I want the energy threshold to be near 0. I don't care if it takes 500 steps and costs me 10 cents to generate. It has to be right.
Versus a script to rename some JPEGs where I'd say, you know what, just give me whatever. I don't want to pay for system 2.
Exactly. Thinking becomes a commodity you purchase based on necessity.
There's another aspect of this I found fascinating, the visualization of the energy itself. The paper suggests that because EBTs operate with this scalar value, they can actually show us where they're confused.
Yes, this is the interpretability win. A standard LLM is a total black box. It just gives you text. An EBT can theoretically highlight specific lines of code in red where the energy remains high.
Wow. That changes the debugging workflow entirely. Instead of me reading 50 lines of code hunting for some subtle logic error, the AI hands it to me and says, look, I'm 99% sure about the boilerplate, but lines 14 and 15 feel really shaky to me.
I'm stuck in a local minimum here. It directs your human attention to the fragile parts. It's metacognition visualized. It's the AI admitting doubt.
Which is strangely humanizing in a way.
It is. It moves away from the oracle model of AI, where it just knows everything, to an explorer model, where it navigates possibilities and reports back on the terrain.
I do want to play devil's advocate for a second, though. The paper is titled, A Pipeline for Assessing. They haven't solved AGI here. They are proposing a way to measure if this architecture works.
That is a crucial distinction, yes. They have validated the architecture on specific tasks, but scaling this is hard. I mean, calculating energy for every possible output is computationally very heavy. Training these EBTs is historically more unstable than training standard transformers.
And the checker model in algorithm 4, I mean, if the checker is dumb, the whole system breaks, right? If the checker also loves dot rows, because it also hallucinates, you just have two idiots agreeing with each other.
The blind leading the blind scenario, absolutely. The efficacy of this entire pipeline depends on the checker being robust enough to spot the local minima that the generator fell into. Yeah. If they share the same blind spots, the feedback loop is useless.
So it's not a magic bullet, but it is a map.
It's a map out of the stochastic parrot era. It gives us a concrete mathematical framework for reasoning that isn't just predicting the next word really well.
It effectively redefines what correct means for an AI. Correct isn't just matching the training beta anymore. Correct is minimizing energy in a logical landscape.
Precisely.
You know, as we wrap this up, I'm thinking about that transition from wrong to right in the landscape. That moment the ball rolls out of the rows, dip and finds dot arrows.
Okay.
The paper defines passing the assessment as the model successfully updating its prediction after feedback. It self-reflects, realizes the energy is too high, and works to lower it. If an AI can do that, I mean, if it can observe its own internal state, acknowledge a conflict, and then deliberately expend computational energy to change its position, are we just splitting hairs by calling it energy minimization?
That's the big question, isn't it? At what point does the math of gradient descent become indistinguishable from the psychology of changing your mind?
When does a correction become an epiphany?
If the behavior is identical, if it stops, thinks, and corrects, maybe the mechanism doesn't matter as much as we think it does.
That is a thought that is going to keep me up tonight. We'll leave you all to ponder your own energy landscape.
Keep minimizing those local minima.
Thanks for listening to The Deep Dive. We'll catch you on the next one.